Can you hear me on Zoom?
Yeah.
Great, thank you. Why? Huh. One, two, one, one, two. 1, 2, 1, 1, 1, 2. I don't know. I have some trouble connecting my laptop to the screen, and also the microphone doesn't work. 1, 2. Can you hear me? No. Wait, it doesn't work. Oh yeah. 1, 1, 2. 1, 2. Huh. 1, 2, 1. Does the microphone work? Yeah. Okay. Welcome everyone again. Great to see more of you for the quiz now today. So did everyone finish? Anyone who hasn't finished? Okay. Oh, okay. But yeah. If you have any trouble or there's anything serious, come talk to me. So in the office hours, I'll send an email. So, but otherwise, I hope everyone is okay with the programming assignment. What else? So the quiz today, the format is the same as previously. So there's nothing that's changed. Modules 3 and 4, 40 minutes. Any questions on that? Yeah.
When did the project grade come out?
When will the project grades come out? Yes, my TAs have started grading already. Projects 1. I have to check with them. I don't know if they finished already. So let me get back on that. Yeah, and I had also I know there's a few things to manage, few pieces to manage also. So I had some trouble hiring a second grader. From the university, the payroll department gave me a headache on that. I wanted to hire somebody. They said they couldn't hire them, so I was going back and forth with them. And in the end, I had to hire somebody else. So we are a bit behind with grading in general because of that. So I apologize for it. But now I managed to hire finally someone. So we'll get up to speed with grading also for the quizzes. For the first quiz. Any other questions on this quiz? No? Oh, yeah. You can use your own notes. Yeah. It's an open book. You can use your own notes. You can use the slides on the laptop. You can use a textbook, for example, a PDF of the Russell Norvig textbook. Yeah, I knew that. Yeah. The lowest score will be dropped. Yes. No, it's open book for you can use the slides and the PDF of Russell and Norvig, but not the internet. Yeah. Okay. Yeah. Oh, and also, so maybe I should specify a bit more. So no chatting on social media. So we don't allow basically among each other, basically. So again, I do care about that. I hope I won't, I'm trusting that, none of you are kind of exchanging sort of answers during the quiz somehow through my mobile phone and so on, mobile phone text messages. Okay, but otherwise it is open book, so you can use any notes and anything on the slides. Okay. Let's get started. Let's go for half an hour and cover a few more topics in a knowledge presentation, because we're gonna at 6 we hopefully start in the quiz. If you remember last time we gave this example of the car, this knowledge base about the car, where basically we had a situation where the battery was okay and the bolts okay, which implies that headlights work, battery okay and a starter okay, and the gas tank is not empty, means that the engine can start, and so on. Some more rules like engine starts and not a flat tire means the car is okay, headlights work, but the car is not okay. And we saw how sentences 1, 2, and 3 are background knowledge about cars in general. These are rules that we have, whereas sentences 4 and 5 here are observed knowledge about a particular situation. And using both the background knowledge and our observations, we can make inferences. We can try to find out what's the reason why the car isn't working. Is it, is it because the bolts are not okay? Is it because the engine didn't start? Why did the engine didn't start, and so on? So we can do these kinds of things. And the same thing we have with the Wumpus scenario. And where in our Wumpus world, we had the cave, we had the grid world, we had a monster there that we didn't know where it was, and we had those kind of pits where we didn't want to fall into the pits. So we had for example, Boolean value Pij, which is true if there is a pit at location Ij. We have Bij, which is true if there's a breeze at location Ij. So we can write them as, for example, not P11. There's no pit at 11 because we started and we didn't see anything. There's no breeze at B11, but there was a breeze at B21 when we went there. So that means that, and then we can deduce that, for example, a square is breezy if and only if there is an adjacent pit. This was the rule that we had in the game, which is, for example, codified as there's a breeze at B11 if and only if there's a pit at either P12 or at P21. There must be a pit nearby, adjacent to that square. So this is how we code it up in a logical statement. This part here, we'll write this whole thing like that. So for that particular state, and this holds for all the states. And to remind ourselves again what we mentioned about logical entailment, and entailment again means that if we have a knowledge base which has a set of sentences and we're given alpha, which is an arbitrary sentence, we say that the knowledge base entails alpha, which is written as this knowledge base entails, this red sign entails alpha, if and only if every model of the knowledge base is also a model of alpha. Yeah, so that's the knowledge base has a much more restricted model because there's more sentences in the knowledge base than just the alpha. There's more, so therefore the models are more restricted. And again, remember the model is a set of all possible states or representations of the world where this alpha is true, where this sentence holds. That's what a model was. Is it clear? This is a reminder. I don't see any questions. Okay. So let's move on. So we have the notion of logical equivalence now that we have to introduce. So logical equivalence is defined as, for example, two sentences, alpha and beta, are logically equivalent, which is written like this: alpha, 3 lines, triple equal beta, if and only if they have the same models, i.e., alpha entails beta and beta entails alpha. And examples of sentences that are equivalent are basically this. So for example, alpha and beta is equivalent to beta and alpha. And this means that, that whatever values we assign to alpha and beta, this will hold, that alpha and beta will be equivalent to beta and alpha. So they will always be true. They will always be true for any assignment of alpha and beta, like this statement here. And the same for this one in red, for example. This is the implication, which actually I've put it in red because sometimes it causes some confusion for some people. Alpha implies beta is equivalent to not alpha or beta. And it's a known logical statement. And this means that it's equivalent. So for any assignment of alpha and beta as being true or false, this thing will hold. The whole thing in red will be true for any assignment of alpha or beta. Same thing for these last two. Does anyone know what these are called? They have a name, yeah? Yeah. Well, De Morgan laws, yes. These are called De Morgan laws. So alpha and beta negated is equivalent. So do correct me. So I should say it's equivalent, not equal, to not alpha or not beta. And similarly flipped for the OR operator. Yeah, the Morgan laws. So these are equivalent again for any assignment of alpha and beta to true or false. These things will hold. And a key observation that one can always replace a sentence with an equivalent one in the knowledge base, and you can make the same types of inferences if you as long as the replacement is an equivalent one. It will be the same thing. It doesn't matter. Okay, so this brings us to the idea of doing Did you have a question? No, okay. This brings us to the idea of doing proofs. So using these types of logical rules to make proofs of various things. So for example, we can basically generate sound, legitimate, or what we call sound statements or sentences from the knowledge base, from the old sentences, basically. And again, sound means that they are correct, that the ones we infer, we reach with our logical statements are actually true and hold true. That's what sound means. Again, and here proof would be a sequence of inference rules that we apply. So we apply multiple rules one by one, we compose them, and then we end up with some sort of inference. So we'll look at several. For example, we'll look at modus ponens, modus tollens, forward chaining, backward chaining, and something also called resolution refutation, which we'll see shortly. So we won't cover all of them today, but we'll start with some of them. Some of these you see come from Latin. They were actually or Greek. I think they were already known to the Greek and the Roman philosophers back in the ancient times. So that's why they have these Latin names. But yeah. There's quite a rich history about it. I'm not too familiar with it, but yeah, you can read online. So let's go into the first one. So modus ponens, what does this say? So this is what modus ponens say. It's actually very simple. So we have two statements here. Alpha implies beta, and then a new statement which says alpha, and from these two we can infer beta. If we are given alpha implies beta, and then we also given alpha, we know alpha is true, then we can infer that beta is true. So let's see it in practice on one of our examples. So again, let's take again our car example. For example, you can apply these kinds of methods on self-driving cars, for example, to try to understand, well, is the self-driving car doing the right thing or not? So, but here it's not even self-driving, it's more of like even like a starting to see if the car starts. So let's see how we apply this. So say we start with the knowledge base. So this is our knowledge base. Then we have in red here, we have the implication. Yeah. So I put it here. Then in green, I don't know if you can see, this one is green here. This is alpha. And from this, we can deduce that the headlights work. We deduce beta. So because we're given that the bulbs are, battery is okay and the bulbs are okay, and that if the battery is okay and the bulbs are okay, which implies that the headlights work, then we can deduce that the headlights actually work. So we just applied modus ponens on this example. Any questions? Oh, good. Nice. So then now we're going to talk about something called. Oh yeah, there's a question here.
In the previous slide, stuff in partial technical implications, correct?
They are still implications. We haven't used them, so you can have more in the knowledge base, more information. You don't use all of it. Yeah. Any other questions? Okay. So now that we saw how modus ponens work, let's try to see some other types of chaining. So let's talk about forward and backward chaining and what they are. So these are basically applied on what are called horn clauses, which are certain types of clauses. We'll come back to them a bit later, but they are basically they're defined basically as either a propositional symbol or a conjunction of symbols, which imply a symbol. So it is kind of implications with conjunctions. These are kind of like it's a more restricted set of clauses we can make. They're sort of they've been used in the literature because they can allow us to apply certain kinds of inference procedures on them, or like that we cannot apply on the general logic. So for example, the modus ponens is complete for horn knowledge bases. So basically, what does this mean? Okay, what does completeness mean? Does somebody remember what? So let's see what was. Let's try to understand this sentence here. So what does complete mean? Completeness. We spoke about it in the last lecture. One lecture ago, 2 lectures ago. Anyone? Yeah.
Be proven wrong.
It cannot be proven wrong. Actually, that's not exactly right. It's something slightly different. Yes. Somebody else? Yeah. Yes, it always finds an answer. Yes, there's my question. So basically, if there is an answer, it will find it. Basically, it finds all the clauses that are basically true. It reaches them. So that's what completeness means. So all the Horn clauses in this case that are true, our inference procedure called modus ponens can reach them and prove them. That's what completeness means, and that's what this line means. Because here again we're talking about Horn clauses which are more restricted, so the only implications using the conjunctions here. That's that's basically why this is complete. And this can be used, so we can use what we call forward chaining, backward chaining to apply them on these like Horn clauses. So and what's very nice that the algorithms run generally in linear time before when we apply these procedures. So we're going to talk about both forward and backward chaining. So let's talk about forward chaining first. So the idea is that we start with our knowledge base and we fire any rules on which we have enough observables to fire them. So basically, if we have something like A implies B, if we have A in the knowledge base, then we fire that up, and basically we deduce B. That's the idea. So every time we have information in the knowledge base, we start firing the rules. So and add the conclusions back to the knowledge base, and we do that until the query is found. So let's see. So this is the idea of forward chaining. So we'll go forward in time from the start of the knowledge base. We go and apply the rules from our observation. So let's see an example. So this is our knowledge base. We have P implies Q. We have L and M implies P. We have B and L implies M. We have A and P implies L. A and B implies L. And we have 2 observations, A and B. Okay, so the task is now to prove Q here. Let me move that. Here we go. So we need to prove Q given this. Okay. So notice how we have P implies Q. We don't have Q on its own. We have to prove Q on its own, basically. That this holds. So how do we do it? How do we do it with forward chaining? So we start from what we're given, from the givens, from these ones, from A and B, from all our observations, and then we start applying these rules one by one, in some order. So we start from A, for example. Again, we're gonna get B as well. And then in the third step, we fire up this rule. So A and B implies L because we have both A and B. And now we derived L. And then we fire up another rule. And in step 4, we fire up this rule. B and L implies M. So then now we deduce also M to our knowledge base. And then, I guess I should have also enumerated them on the side, what we have now. So far, for example, we have A, B, L, M, and P. So here, actually, I didn't go to the 5th one. So then again, we fire L and M, and we deduce P, because we know L and M from before. And then in step 6, we fire P implies Q, and then we're done here. So we simply start from so these are the steps, like this, one by one. So we start from our observations and start firing up the rules up until we reach Q. Okay. Any questions? Is it clear? Okay. Good. So Let's now talk about backward chaining. So now that we did forward chaining. So in backward chaining, the idea is actually to do completely the opposite. So we start from the back, from the goal, and we go back to the beginning. So we start from the end state and we go back. And yes, and we check, for example, if we have to prove Q using backward chaining, we first check if Q is known. And if it's not known, then we start kind of going back with the rules, basically, and try to find out what do we need to prove in order to get to our target state Q. Well, you know, oh, for Q, I need to prove P and R. Oh, and then for P and R, I have to prove something else, like, you know, M and N and O, and then and so on, up until you reach the beginning, basically, you reach your observables. And we have to do two things. As caveats, we have to do this. We have to avoid loops. We have to check if the new sub goal or is already in the goal stack, and we have to avoid repeated work. So, for example, you check if the new sub goal has already been proved true or has already failed. So these are two things generally you have to do. Otherwise, we will keep looping forever, or we'll waste a lot of computation. So let's see an example of this again, of backward chaining. So I'll say the exact same example as before. The same knowledge base, the same observables A and B, and now we have to prove Q with backward chaining. So generally we build a table here. We build something like this. So we build a table of what we have proved so far, what we want to prove next, and also for example, the rule we applied. So if we, for example, so here we want to prove, because we have to prove Q, then we fire up this rule, P implies Q, and then this brings us, we have to prove P. To be able to prove Q, we first have to prove P, right? So so we've applied the first rule already. Then we make another step and we say now that I have proven P from here. No, sorry. So I made a mistake. So we fire up a new rule. So L and M implies P, which means that I have P already proven, but now I have to prove L and M for this because I fire up this new rule, L and M implies P. Okay. And then we fire up a new rule, a third rule. So now, for example, now we again from before. Let me go back again. So we want to prove either. We need to prove either L or M. So say we try to tackle L next. So we have one of these two rules that we have to choose from. So we choose this one, A and B implies L. So we apply it here. This means that now we have to prove. So L is now gone because we have applied this rule. We still have M left, and now we also add A and B because we need A and B to apply this rule. So we still need to prove A and B and M, and now we have proved through this P and L now. And now we fire up a new rule. So for example, let me go back. So where are we in the state right now? So let's see. So we still want to prove A, B, and M, right? So A, B is B here, and M is here. So we want, for example, to fire up the rule for M, which is this one. B and L implies M. And this means that we now have proven P, L, and M, and we still want to prove A and B. Yeah. And we apply another step where we apply the rules A and B here, which are basically our observables. And now we proved A and B, so our stack of what we want to prove now is empty, and we have proved all of these P, L, M, A, and B. And now we're done because we have nothing else that we still have to prove to complete the proof. That's just it might be a bit harder, but does this make sense? Does backwards chaining make sense? Yeah. Yes. 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 So by itself, it doesn't say that by itself. This is a rule. L and M implies, so what we say here, but because L and M can, so just if you take this rule in isolation, it doesn't necessarily say that, because it just means whatever assignment of L, M, and P make this whole sentence true. And for example, you can make L and M to be false, and then it will still be true. Yeah. But proof Q here means that Q has to be true. Yes, Q will have the value of true at the end, because here when we have also here A and B given as observables, this means that A is given to be true, B is given to be true. That makes sense. The observables are true, and this sentence is true, holds, and that other sentence, and all of these hold by means that they evaluate true. Does this make sense? I know it can be, but I think it's an important concept to get. They all have to be true. All of these lines have to be true. Have to evaluate true. Yeah. Have proved. Yeah. So because in the backward chaining process, in the process of applying back chaining and proving Q, we also have proved all these other ones in the means in the process. Over here, or where? Oh yes. Yeah. So you're right. Yes. So basically, our colleague was saying that when we fire up this rule, basically we still don't know. We want to prove P, and then we sort of added it to have proved because we fired up a new rule. But in practice, the chain can break at some point. For example, if you find no way to prove these prerequisites, if you don't find something in logic, then it means it failed. The search failed, so then you haven't proved it. So basically, maybe P wasn't, for example, what you explained here, P wasn't true actually. Yes, that's what it means. So the search can fail. Yeah. I'll stay a bit more here in case anyone has any questions. Yeah. This one here. This one. Exactly. It's just saying if we somehow find L and M, then we basically get P because through this rule, basically we have proof P as long as we find L and M. Yeah. It's I know it's kind of a way to show you exactly step by step. Yeah, but I think you get what I'm talking about. I made it up actually. You know, I made this table like just before the lecture. You know, like so basically, it's to help you. Like in practice, when it's coded, it can be coded in different ways. Yeah, but yeah. Any other questions? Okay. So for a bit of comparison, so forward chaining is basically automatic. It's basically sort of what we call unconscious processing, how some people call it. It's basically we start from the beginning from our observables and we keep firing rules, hoping that we're going to reach the goal state, if that makes sense. And sometimes we can expand in multiple directions, maybe even blindly. Do you remember, for example, uniform cost search? That was an example of basically, you didn't have a target goal in mind. You were sort of hoping at some point in the graph you'll find the goal state, but you didn't have a direction, like a heuristic, for example. So kind of like forward chaining is kind of like that. We don't have a good direction of where the goal state is. Maybe there's a way to put a heuristic on this. That's something to think about. But anyway, backwards chaining is on the other hand, goal-driven. It's completely the opposite. So we start from the goal and we come back to the beginning, try to see what do we need to prove to reach that goal, and we come back to the beginning. So it's goal-driven. It's very appropriate for problem solving, for example. It's actually quite a popular method for doing theorem proofs, for proving theorems, mathematical theorems with these kinds of logic. And actually, these kind of logics are very popular for that. Actually, if any of you at some point, you've done, how many of you have done mathematical proofs? You've done, okay, so quite a few, yeah. So these are the kinds of AI algorithms that can do mathematical proofs with these kinds of logics. So basically, then in that case, you don't have to do it yourself. The computer can do it for you, and sometimes go over like really long and complex proofs with these kind of logical methods. And for example, backward chaining could be exactly one way to do it. We start from the target, and you come back to the beginning. So, yeah. I'll skip this for a bit. Again, this is basically saying like a general slide on a general problem. What we have is that we have a knowledge base, which is a set of sentences, and we have alpha sentence. And then the question is, does the knowledge base entail alpha? Can we say something about alpha from given this knowledge base? That's our Let me introduce you now to important concepts of satisfiability and viability. Validity, not viability. So a formula is satisfiable if it is true under some assignment of the variables. So x plus 7 equals y is satisfiable for x equals 1 and y equals 8. So basically that means that there is this formula is satisfiable because there is an assignment of x and y which makes it true. Whereas a formula is valid, so validity is basically true when over all the assignments to the variables. So for example, this is a valid formula, x plus y equals y plus x, because for any values of x and y that we give, this will hold. This will be true, not only for one or some of them. Does this make sense? And this is true in general for any, and I put this in brackets, for any more mathematically for any group that is commutative, because this plus symbol is commutative. So for any sort of operator plus that is commutative, this will hold. This formula will be valid. Okay. So I think I would love to go a few more slides, but I think I'll have to stop here and sort of give you. Let's take a 6-7 minute break, and then we're gonna start a quiz. Okay. Yeah. It's fine. Yeah. Thank you so much. Thank you so much. Okay. Yeah. Yeah. Oh, I haven't managed to look. I think so. March 20th. Gotcha. Let me look into that. Actually, I haven't managed to look into it. I'll confirm. In a few days. Yeah.
And then the format of the final is similar to the quizzes or different or.
Could be different. No, actually, it won't be the same. It will be harder. Like put something like harder than the quizzes. Yeah. That's the final.
You can still answer the question again.
It's okay. Yeah. I know. Yeah. It's okay. Really, don't worry. Like it's. I know. It's. No, don't worry. No, it'll be harder, but not. Yeah. Don't worry, Nicholas. Don't worry. Yeah.
expected how to? Are you expected to memorize concepts?
No, memorize. You can use it. It's open book for the quizzes. You can use it after the final. We'll get to that. Don't worry. So far, you don't have to memorize. Oh, why did I stop sharing? Sorry, I stopped sharing by mistake. Okay. No, it's not. Oh, yeah. The same as last time. Yeah. And what about the people on Zoom? Fatema again. Fatema. Yeah. She will email them.
Yeah.
Okay. Yeah. Oh, I might actually. Yeah. Damn. Oh, I don't think I have. Wait. I don't have. Sorry, I don't have a pen. Sorry, do you have a pen? Does anybody have an extra pen for our friend here? Yeah. Oh, there you go. Yeah. Okay.
Should I ask you the same?
Yeah. Yes. Okay. Listen. Okay. Okay. Yeah. All these. Yeah. Just pass them on. So don't start yet. But yeah, let's just. I'll bring some more. Yeah, pass them on. How many do we need here? You need to pass them there. Thank you. And pass them on. There's one more needed there. And here. Yeah. Does everyone have assignments? Yeah, quizzes, okay. So write your name and student ID on the, next to your name, as last time. We're starting very shortly. Okay, shall we get started? Yeah, okay, let's start.